You know all the physics concepts, right? But you're still dropping mysterious, painful marks on past papers. Well, today we're instantly upgrading your final minute revision into a high-scoring system for Cambridge Physics 0625. We're ditching the generic textbook reading. Instead, we're building a bulletproof exam strategy using real, syllabus-specific data interpretation. We're going to hunt down the exact traps examiners set, show you how to spot them, and secure those grade-defining marks. Let's dive right in. Take a really close look at this pie chart showing China's electricity generation in 2020. Thousands of students drop critical marks right here, immediately. Why? Because they make one tiny, painful assumption instead of actually calculating it. You know how it is in the exam room. Adrenaline is pumping, the clock is totally merciless, and it's so tempting to just eyeball a graph like this. You might look at that missing sector for gas and think, it looks like a little less than half. But guess what? That instinct is exactly what the examiner is banking on.
So what's the hidden mistake that's literally costing you the grade boundary on what looks like a ridiculously easy question? Well, it looks like basic math, but if you don't actually physically subtract the given known values from 100, you risk losing incredibly easy method marks under that exam timing pressure. Cambridge Physics isn't just checking if you know what a pie chart is, right? It's testing your rigorous scientific process. If you skip showing that mathematical subtraction step to find the missing piece, you're just leaving your final grade entirely up to chance.
And here's the proof. This is direct, unfiltered feedback from the Cambridge examiners themselves. They explicitly state that common mistakes include missing units, rounding too early, and wrong variables. This is exactly why ordinary revision fails. It completely ignores the exact little things examiners are actively hunting for and just focuses on the core concepts. Listen, you could literally memorize the entire physics syllabus, but if you write down a naked number without a unit or you round off a number halfway through your calculation, boom, you immediately cap your mark band. We have to completely change how we approach every single answer.
To totally bulletproof your answers, we need to apply a specific 4-step framework to every single data interpretation question. Step 1, identify the core physics concept. Step 2, extract the precise evidence or data from the source. Step 3, apply crystal clear scientific reasoning to connect that data to the concept. And finally, Step 4, package the whole thing using exact examiner wording. If you just filter your exam panic through this system, I promise you, you will never leave an easy mark on the table again.
Now, in just a moment, I am going to show you the exact examiner clue that changes this entire energy calculation completely. It's a total game changer. But first, you need the framework that actually makes that hidden clue obvious. It's not enough to just passively know the steps. We have to actively map out the data using our new system. Because if you skip the mapping, you're going to fall right back into the trap. So let's slow things down, look at the evidence, and build our answer exactly the way a top band student does. All right, let's decode the evidence directly from the chart. We're applying step 2 of our framework right now, extracting the data. We've got these highly specific percentage segments, 2.1 for nuclear, 3.2 for other sources, and 2 large segments of 23.6% representing renewables and coal. Notice how incredibly precise these numbers are? The syllabus absolutely expects you to use every single decimal point provided in the source material. Whatever you do, do not round them up in your head. Write them down exactly as they appear. Your calculator is your best friend here, but your written paper is your proof.
So adding these up gives us 52.5%. That represents the total of all the known non-gas sectors. And guys, this brilliantly illustrates exactly how we secure our method marks. By just writing out the super simple addition equation, you're basically shouting to the examiner, hey, I understand that a pie chart represents a whole, and I'm quantifying the known parts. Even if you somehow completely mess up the final subtraction because your finger slipped on the calculator, showing this clear scientific reasoning will very often earn you partial credit.
Then, by subtracting our known total of 52.5 from a complete 100%, we hit our critical target. Exactly 47.5% of China's energy was generated from gas. The absolutely crucial point here is that this is not an estimation. It's an exact, mathematically derived figure. We took the concept of a whole, we used specific evidence, applied our mathematical reasoning, and arrived at a highly accurate number. But wait, having the number is only half the battle. How you actually write it down on the page changes everything.
Check out this comparison to see how this builds your final score. Spot the error on the left. The panicked student answer simply says 47.5 from gas. It completely lacks units and it lacks context. Like, is it 47.5 gigawatts, 47.5 power plants? Who knows? Now look at the top band answer on the right. It secures the mark by being beautifully, rigorously precise.
47.5% of electricity generated from gas. It flawlessly applies step 4 of our framework, examiner wording. It includes the unit, the percentage sign, and explicitly states what that percentage actually represents.
Okay, now for an interactive challenge to really put this system to the test. We're escalating the difficulty here. Let's look at question 20 from our source. We're given a total electricity value of 75.5 terawatt hours for the first 3 months of 2020. But here is our target, explicitly demanded by the syllabus. We have to give our answer to exactly 3 significant figures. Using our previously calculated 47.5% for gas and the given 23.6% for renewables, we need to calculate the exact volume of electricity produced by each.
I want you to literally pause and predict your answer right now. Seriously, grab a calculator. Pay strict, meticulous attention to that syllabus requirement for 3 significant figures. Remember that examiner feedback we looked at earlier about the deadly traps of rounding too early and missing units? Keep that in mind. Calculate the terawatt hours for gas, and then calculate the terawatt hours for renewables. Do you have your numbers written down? Okay, let's see how you did.
Let's look at the source material for question 20 again and see if your calculation successfully dodged those rounding traps. To find the electricity from renewables, you needed to calculate 23.6% of 75.5 terawatt hours. If you punch 0.236 multiplied by 75.5 into your calculator, you're going to get a very specific, long result. But the real question is, how do you write that result on the final line of your exam paper? Because this right here is exactly where the grade boundaries are decided.
A flawed answer leaves that long, raw decimal directly from the calculator display, something like 17.818 terawatt hours. Now, while that's mathematically accurate to the raw data, it totally fails the syllabus constraint. The examiner-approved top-band response strictly evaluates that number and rounds it to 17.8 terawatt hours to perfectly satisfy the 3 significant figures rule. If you wrote 17.818, you just ignored the specific examiner wording required for this paper. Precision in physics isn't just about decimal places, guys. It's about following the exact formatting rules of the discipline.
And this exact same strict attention to physical scale and data interpretation isn't just for pie charts. It's completely mandatory when you're evaluating other types of visual models, like Sankey diagrams. A Sankey diagram, as defined in our source, shows all energy transfers taking place in a process, where the thickness of the arrow literally determines the amount of energy involved. Just like you can't ignore the 3 significant figure rule, you absolutely cannot ignore the proportional thickness of a Sankey arrow. It is visual data that requires the exact same rigorous mathematical interpretation.
But wait, here is the ultimate unresolved problem that catches even the absolute best students totally off guard. What if your math is completely perfect? Your units are flawless. You followed the significant figures rule to the letter, but your interpretation of the specific command word is entirely wrong. I'm telling you, calculating the correct number is utterly useless if you fail to respond to the specific action the examiner requested. Did they ask you to state, calculate, determine, or evaluate? Each and every one of those words requires a vastly different structure to your answer. This is the diagnostic cliffhanger we face. Command words strictly dictate whether your perfect calculation actually earns the final mark. You can use our 4-step framework flawlessly, but if you mismatch the examiner's vocabulary, you break the system. Understanding these exact vocabulary constraints is the hidden key to unlocking that top mark band.
You've mastered the data extraction and calculation traps today, which is huge. But you absolutely must understand those vocabulary constraints to secure your final grade. Our next explainer provides the full revision map, revealing the hidden cause behind lost marks, even when your physics is mathematically perfect. Until then, ask yourself, if you calculate perfectly but fail to evaluate, did you really answer the question at all? Don't leave your final grade to chance. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the next explainer on your screen right now to master those command words, and I'll see you there.